The third lesson in our thermochemistry unit is on the quantitative aspects of heat transfer. In our previous lessons, we have discussed heat transfer as always being something that occurs from objects of warmer temperatures to objects of cooler temperatures. In this lesson, we'll look at some of the measurements and the calculations that we can do along with this idea. The learning targets in this lesson, just two of them. We want to be able to relate the amounts of heat absorbed and heat released during energy transfer. And then we also want to use heat transfer data or calorimetry data in order to calculate unknown quantities during this heat transfer. So let's just start with a hypothetical experiment. Let's say that we heat a 50 gram cube of an unknown metal to a temperature of 98.2 degrees Celsius. We place the metal in a 75 gram sample of water at 21 degrees Celsius. The metal and water reach thermal equilibrium at 23.4 degrees Celsius. Notice the similarity to the experiment that we just completed in class, the specific heat of the unknown metal. This is the exact same situation where we have a metal, we know its mass, we know its initial temperature, we have some amount of water, which we know its mass, we know its initial temperature, and then we place the metal into the water, we let it reach thermal equilibrium. Well, when this happens, the metal is going to release energy or lose energy, whereas the water is going to gain that energy or absorb the energy. And this will continue to happen until they reach thermal equilibrium at, in this case, 23.4 degrees Celsius. If we were to calculate the heat of the metal, actually we wouldn't be able to do that because we don't know what the specific heat is yet, but we know it's releasing energy, so we know that the Q value for the metal is going to be less than 0 or negative because that's an exothermic process if metal is the system. For the water, it's going to be positive because it's absorbing that energy. It's endothermic. If we assume or approximate that there is no heat that is transferred from the container or to the container or any of the other surroundings, in other words, it's only going from the metal to the water, this means then that the heat that is absorbed by the metal, the Q value of the metal will equal the negative of the Q value for the water. Or another way of writing that, we can say that if we add those two values up, they're going to equal 0. In other words, the net heat transfer is always equal to 0 because whatever is released by one substance has to be gained by another and vice versa. So here's what we can say. We can say that during heat transfer, the energy that is released by one object must be absorbed by another object or objects. And we can always say then that the heat that is absorbed plus the heat is released is equal to 0. And this is because one of these is going to be negative because we are releasing energy, so exothermic, so Q value will be negative. So that's really the entire principle of that first learning target. Now we're going to use this idea in order to do some calculations to find unknown data. So let's just revisit that same experiment that we had in the first slide. We're going to try to calculate the specific heat of the metal. So just to review here, we have our metal. It's at an initial temperature of 98.2 degrees Celsius. The water's initial temperature we know, and then we can see that the two objects, the water and the metal, end at 23.4 degrees Celsius. Here's what we know. We know that whatever the heat absorbed by the water is, plus the heat that's released by the metal is going to equal 0. And here's how we would calculate those Q values for both of them. Now notice the use of the subscripts now, the subscript W being for water, the subscript M being for the metal. This is still the same equation we've always used. Q equals M delta Tc. We've just now included subscripts to be able to differentiate between the two. If we think about these two equations, the two equations with Q in them, the only one we can actually use to start with is the one for water because we don't know what the specific heat of the metal is. So we're going to calculate QW. That's the first thing we'll do. And we can just plug in our values. There were 75 grams of water. If you would go back to that first slide, you would see that it's listed on there. The change in temperature, the final minus the initial temperature, and then times the specific heat of water. And that is going to give us a value of 750 joules. So that is the amount of energy that the water absorbs, or that is QW. We know that if we add QW and QM, again QM being the heat absorbed by the metal, that's going to equal 0. Well, what that means then is QM has to equal negative 750 joules. So when we know what QM is, we know the mass of the metal, we know the change in temperature of the metal, so now we can find the specific heat of the metal. So we solve our equation for the specific heat, we substitute in the numbers that we have, the negative 750 joules that we just established up here, the mass of the metal was 50 grams, and then the change in temperature, remember it's always final minus initial, so 23.4 minus the 98.2 degrees Celsius. And now we can calculate it, and this gives us a value of 0.20 joules per gram degrees Celsius. Let's look at another example. A piece of 16.5 grams of chromium is heated to 100.0 degrees Celsius. It's dropped into 55.5 grams of water at 16.5 degrees Celsius. The final temperature of the metal and the water is 18.9 degrees Celsius. What is the specific heat capacity of chromium? And we're told to assume no heat is lost to the container or to the surrounding air. So this is really the exact same problem that we just did. We are trying to find the specific heat of chromium, just like we were before. Now in the one before we didn't know what the metal was, but it still makes no difference. It's the same problem. What we can find first is the heat that's absorbed by the water. Because we know the water's mass, we know the water's change in temperature, we know its specific heat, we can find the heat absorbed by the water. So just plugging in the numbers, 55.5 grams times the change in temperature of the water times the specific heat of water, this will give you 560 joules. Now that we know the water is going to absorb 560 joules, we can find how much energy the chromium released. Well, that's going to end up being negative 560 joules. 560 joules, it's going to be the opposite of QW, negative because it released it. Now that we know the amount of heat the chromium released, we can find the specific heat of the chromium. We're just going to solve this equation for the specific heat. So divide both sides by mass and change in temperature. Then we can substitute in our values. Remember the negative 560 joules from the previous slide, that's the heat that's released by the chromium. 16.5 grams times the change in temperature, you can see final minus initial. And this will give us a value of 0.42 joules per gram degrees Celsius. Here is a different problem. We're not asked to find a specific heat here. We're told that a piece of iron, 400 grams, is heated in a flame and then dropped into a beaker containing 100 grams of water. The original temperature of the water was 20.0 degrees Celsius, and the final temperature of the water and iron is 32.8 degrees Celsius after thermal equilibrium has been attained. What was the original temperature of the hot iron bar? And again, we're told to assume no heat is lost to the beaker or to the surrounding air, and we are given the specific heat of iron. You can see it here. So in this problem, again, because we know everything about the water, we know its mass, we know its change in temperature, we know its specific heat, we're going to want to find the heat that's absorbed by the water. Just plugging in our values, so 1,000 grams of water times the change in temperature times the specific heat. That gives us 53,600 joules for the heat absorbed by the water. Well, that tells us then that the iron released 53,600 joules of energy, so QFE would be negative 53,600. Now we can find the change in temperature for the iron because we know the heat that it released, we know the mass of the iron, we know its specific heat, so we can solve this for delta T, just dividing both sides by the mass and the specific heat. And we substitute in our values and we can calculate, and this gives us negative 298 degrees Celsius. That's the change in temperature. Now notice this isn't what we're asked to find yet. Okay, we're not asked to find the change in temperature. We want to know the original temperature. So we need to find the temperature of the iron before we put it in the water. So we know that the final temperature of the iron minus its initial temperature will equal the change in temperature. So the final temperature was 32.8 degrees Celsius minus its initial temperature. That's going to equal the negative 298 that we just found up here. So TFE has to be 331 degrees Celsius was the initial temperature of the iron. Alright, so there were just a few examples of using the data to find unknown quantities. There are a couple of review questions here. Well, first review question, we want to describe the relationship between the energy absorbed and the energy released during a heat transfer. We know that during any heat transfer, the energy that's absorbed by an object must be released by another object or objects. Thus, the total energy transferred is equal to 0. In other words, Q released plus Q absorbed has to equal 0, or they're equal to the negative of each other. You can think of it that way as well. Here's a practice problem to work on. We have a 245 gram cube of copper, and we're given its specific heat, and we're told that it's heated to a temperature of 195.2 degrees Celsius and placed in a sample of water at 19.4 degrees Celsius. When thermal equilibrium is reached, the copper and water have a temperature of 23.9 degrees Celsius. We're asked to determine the mass of water in the sample and assume that no heat is lost to the container or the surroundings. So notice in this problem, this one's different than any of the ones that we did earlier, is we can't find the heat absorbed by the water first because we don't know its mass. But we can find the heat that's released by the copper. Because we know the mass of the copper, we know its change in temperature, we know its specific heat. So we can plug in our values there. Mass times the change in temperature times the specific heat. And that will give us a value of negative 16,200 joules. And recall it's negative because it's releasing energy. Now that we know the energy released by the copper, we can find the energy absorbed by the water, which would be positive 16,200 joules, the energy absorbed by the water. So once we know that, now we can find its mass. Because now that we know its heat, we know the change in temperature, we know its specific heat, we can just solve it for mass. And we can substitute in our values like we have, and we get a mass of 860 grams.